Welcome everyone to today's Foxconn Quantum Computing Seminar. Today we have the pleasure of Llorenç Escolà-Farràs, who will be talking about extended non-local games and its applications to cryptography. So Llorenç is a final PhD student at QSoft and the University of Amsterdam. He did basically he had bachelor's degree in physics and math at the Autonomous University of Barcelona, and has a master's from mathematical physics from Tübingen. And his current research is focused on quantum communication, with some emphasis on non-local correlations and quantum position verification. So, Llorenç, the floor is yours.
Yeah, thank you, Gelo, for the introduction, and also for inviting me to give the talk. That was a pleasure. So today I'm going to talk about a paper that is called Lossy and Constrained Extended Non-Local Games with Applications to Cryptography, in particular bit commitment, quantum key distribution, and quantum position verification. And this is a joint work with Florian Spielmann, who is my supervisor. And well, as Gelo said, I'm from QSoft and the University of Amsterdam. So without further ado, I'm going to get started. I'll go first to an Outlook. And why can I pass the slides? Okay, now. So first, I'm going to talk about general non-local games, and then go through the NPA hierarchy, which is a way to analyze them and upper bound the optimal winning probability for non-local games. Then I'm going to go to linear programs and their analogous, which are semi-definite programs. And I'm going to talk about extended non-local games, where are non-local games with a quantum referee. And then there's also an NPA hierarchy for those games, which is called the extended NPA hierarchy. And then I'm going to add laws and constraints to these games and show applications that we could find among those: quantum position verification, relativistic bit commitment, and quantum key distribution. And of course, feel free to interrupt me at any point if you have questions, so that I make sure that we're on the same page and you know what I'm talking about and all the concepts are as clear as possible. Right. So first, non-local games. So they consist on a referee and two players that are two collaborative parties, Alice and Bob. And they have some black boxes that they can use to reproduce certain correlations. And then the referee is picking X and Y according to some probability distribution Q of X and Y. And then he sends X to Alice and Y to Bob. And then X and Y here are going to be picked from a finite set. And they have to answer A and B, also from a finite set. And well, they win the game if certain condition is true. So if a function that depends on the inputs and the outputs that can take two values, 0, 1, it takes the value 1. So it means you have a winning condition. If it's fulfilled, you win. Otherwise, you lose the game. Okay, so the thing is that if they use quantum resources, they can share a quantum state, namely psi AB, shared by Alice and Bob. And the most general thing that they can do, if they have to answer something classical, is to perform a POVM, positive operator valued measurement. So depending on X, Alice is going to do something and answer A, and similarly for Bob, a POVM, depending on Y, is going to answer B. So S, from now on, will be a strategy. Strategy is what they agree before they have to play the game, which is picking a state and which POVMs they pick. So given this strategy, we can compute the average winning probability. And the probabilities, according to the laws of quantum mechanics, of getting outputs A and B given inputs X and Y, are going to be given by this expression. You just take the sandwich with the operators applied to the state. And now the average winning probability is going to be given by averaging over X and Y and taking those guys that you win the game and the probabilities that you can correlate and you can reproduce. And well, we just say that omega star is the optimal winning probability, taking the supremum over all possible strategies that you can take. Is everything clear so far? If I can get
sorry.
feedback, I will assume.
Sorry, can I ask a quick question?
Sure thing.
So, yeah, in the summation of omega, why do you put the winning condition there? I mean, winning
Yeah.
condition is a condition that will tell you win or not win. So how do you why do you specify in the inside the summation?
Why do I specify? Because I can just say also that I'm summing over x, y, a, b sides that this is true. But here, like the other ones, they are not going to contribute if you don't win the game. So only the times.
Yes. Oh, so I see. So only
I have a bit of trouble.
Sorry.
I have a bit of trouble hearing you. I hear some background noise.
Sorry, I'm in some kind of a noisy place.
Okay, no, yeah, go ahead.
So it means that you just specify the condition you want, and you just
Exactly. So you
okay.
first specify the condition, and then you sum over the ones that give you a winning thing.
I see.
So,
Okay.
so this will become more clear in the next slide, because now I'm going to talk about the CHSH game, and here.
I see. Okay,
So that's the most known example of a non-local game, where now we have this scenario: referee Alice and Bob, and they both get binary inputs, so 0, 1 from both sides, and they also have to output either 0 or 1. And now the winning condition is 1 if and only if this condition is fulfilled. The XOR of the outcomes, A plus B, has to be the product of the incomes. That you've probably seen at some point before. It's like the most known example. And then this condition, which is like the thing that you were asking before, takes value 1 if and only if this is true. Okay, so it is known that the optimal winning probability for this game is given by this expression that is 1/2 plus 1 over 2 square root of 2. And this is roughly 85%. Okay, so the thing is that when we want to compute the optimal winning probability of a non-local game, we have to take the supremum over like all the possibilities. But the thing is that this supremum is like over all the dimensions. You can pick any arbitrary dimension for quantum states, and you can pick any arbitrary POVMs, measurements that Alice and Bob might do. And the thing is that now you want to sort of optimize over something that is like any possible dimension. That's like a really hard thing to do. So, but there is a way to find an upper bound to it. And the way is like as follows. It's the so-called NPA hierarchy, where you can find as a hierarchy of upper bounds, like say omega 1 and omega n, that they are always greater or equal than the previous one. And the thing is that each of them can be computed with a semi-definite program, which I will introduce later on. But the thing is that this, you can just like put your problem, put it in a computer, and then get a number out of it. Because there exists an efficient algorithm for that to compute semi-definite programs, and you can find an upper bound to the optimal winning probability. And not only that, you can find upper bounds, but the thing is that this hierarchy is complete in the sense that it converges to the optimal value, to the true value, when n goes to infinity. And worth to mention, in most of the cases, level 1 or level 2 are already good enough to give you the optimal value, which is like something very, very nice. So, yeah.
It looks to me the winning strategy also depending on the condition V in principle.
Yes.
So,
Yes.
but your strategy do not specify V will be chosen. So, it means you specify V first and then find the strategy.
Exactly. V is just a description of what is the game. What do you have to do to win the game?
Okay.
Yeah, V is actually like, if I go back to the CHSH, the game is defined like V says like when you win and when you don't win, right? So it's like, what game am I playing? So I have to play the game that I have to produce outcomes such that they fulfill this relation. So the V thing, the V function is just like saying, okay, this is the game. So V completely specifies the game that you're playing.
Oh, I see. Okay, good. Thank you.
And well, now there's a way to find like recursively upper bounds. And the way to compute them is by semi-definite programs. And before to go to semi-definite programs, I want to do a quick recap of linear programming because it's going to be sort of an extension of linear programming. And that is something that probably more people have seen, linear programming, which consists on the following. You have to find a real number in n dimensions such that maximizes a certain quantity, which is linear. This is like the inner product of a fixed vector c times x, and you want to find its maximum. And the thing is that then you will restrict it so that it fulfills certain linear inequalities. Here, A is a matrix, and its dimension is as many inequalities as you might have. And then you also restrict it to be like positive real numbers. So for instance, if that was an optimization over the real plane, R2, so we would have x1 and x2. And then depending on the number of constraints, you would have a feasible region. And you know that the solutions should be in here because we're optimizing over like the guys that fulfill this condition. And moreover, we know that the optimal will be given by one of the extremal points of the convex polytope of the feasible solution. And the thing is that there exists an efficient algorithm, meaning that can be run in polynomial time, to find the optimal value. Okay, now we're going to consider a similar problem, which is going to be semi-definite programming, SDP for short, whose goal, instead of finding a vector, is going to be finding a matrix such that maximizes the following thing. So the trace of C times X, and that's sort of like a generalization of an inner product for matrices. So that is linear as well, subject to a bunch of linear constraints. And also that we have that X is a positive semi-definite matrix. And now instead of optimizing over R2, we're going to optimize matrices that are in the cone of the semi-definite positive matrices. And the thing is that also exists an efficient algorithm for this kind of problems, meaning that it runs in polynomial time and it can give you the solution up to any arbitrary precision that you might have. So you set precision epsilon, and then you're going to have a solution that is within the precision epsilon and in polynomial time, which is nice. Any questions about that? Okay, if not, I will go ahead. So I will show how to construct the first level of the NPA hierarchy that I mentioned before, that upper bounds the optimal winning probability. So assume that we have a non-local game, and now I just labeled all the possible inputs, like x1 to xm, and same for y, y1 to ym, and similarly for a1 to al, and let's say that there are also L outputs. And the thing is that we have a strategy, and instead of now considering operators that act on a tensor product space, we're going to consider something slightly more general, which is operators that commute. And in fact, it happened to be the same that operators that commute and tensor product operators for finite dimensional, they give the same statistics. So first I'm going to restrict only to these operators. And now, look, we have that the winning probability is given by averaging over x and y, like whenever you win the game, condition B, and then times this guy. Now we're going to consider the following set of vectors, which is like the state that you use. And then these guys, we're going to consider them to be projective operators, because like without loss of generality, you can do that by, if necessary, extending the Hilbert space. So don't get scared about this expression. First, what we do here is to take a quantum state. And now we're just taking all the possibilities, applying the operators to the state. So first, we're going to see what Alice can do to the state. So like the actions that taken by Alice. And now the actions that Bob can do, like apply to the state. So it's like those guys in here. So here it's just all the possible combinations that we have when we consider a strategy, when you apply them to the state. And now we construct the Gram matrix, and the Gram matrix is the matrix that has like entries ij, simply like the the inner product of vectors vi and vj. Okay, so this Gram matrix is like positive semi-definite by construction. And well, I'm going to construct it. So I'm just going to put all the vectors here on the top and the vectors here on the left, the transpose conjugated vectors. And I'm just going to take inner product between all of them. So I'm going to construct this matrix. And first I take the inner product between these two guys. So this is going to be psi. And then I'm going to take the inner product between this guy and this guy. So that's going to be psi a. And then continue so on and so forth. And then I'm going to take the inner product between this one and this one. So I'm going to have this guy in here and so on and so forth. And I will continue with the next row. So this guy times this guy and so on and so forth, right? And here I just complete all the matrix by taking all the possible inner products between these vectors. And now notice that this entry will correspond to the probabilities that we have here to compute the winning probability. So let's have a look at this matrix. This matrix is J1. So observations. First of all, we need this matrix to fulfill certain constraints. So the first one is that this guy is a quantum state. So it needs to be normalized. So first constraint that we have is that this guy has to be 1. Moreover, if we have like the sum over these elements that are here, since these are like probabilities of obtaining A given X, if you sum over all the possible outcomes, the probabilities need to add up to 1, right? So that's another condition that we had, a linear condition that we have over the entries of this matrix. And that similarly applies if we just sum like some of the marginals of Alice's probability. So if we sum them all, we have to have the probability that Bob outputs B, because we're summing over all the possible outcomes that Alice might have. And because of the normalization of the probabilities, this has to fulfill that the marginal probability is Bob's probability. And what else? We are going to consider projector operators. So it means that when we multiply projections onto different spaces, A and A prime, this needs to be 0. But if we're projecting onto the same space, the projection square has to be itself. So we need also these constraints on these guys that we have over here, that if we project into two different spaces, it has to be 0. And finally, we have another consideration that these guys have to commute. So AB has to be the product of BA as well. So now we have a bunch of things that are linear that we impose to a Gram matrix that is positive semi-definite. So we're going to do the following. We're going to maximize. Yeah.
Is there any constraint on the choice of A that must be sum up
the
to
thing is that
identity?
Yeah.
No, it doesn't
here,
have to.
yeah, that's the thing, right? If that sums to the identity, we're going to have that this is 1.
Okay.
Right?
Yeah, I'll say.
Yeah.
So it really gives you the identity if you just sum
Yes,
the
exactly. It gives you the identity, and since this gives you the identity, this will be this value, and this value is 1. So I'm already imposing that here. And also, like, this applies here, right? Because if you sum everything here, that sums up to the identity, and that's why you have just B here.
And okay, and how about if A and B are not commuting?
No, the thing is that if they are like strategies that Alice and Bob perform, they have to be commuting because they act on different spaces.
Oh,
Right?
I see. I see.
So that's the non-locality thing. If they are not commuting, that means that they can act on the same like total space. And then if you can act globally, you can just win the game because like you have all the information. So that's the fact that captures that they are separated, that
I see.
these two guys commute.
Okay, good. Thank you.
Thank you. More questions about that? Otherwise, I will go to the next slide. All right. So we want to maximize this quantity, and by properly defining C, we can just have like taking the values that we have in the matrix J1, and this I'm gonna call it omega 1, and recall that this we obtained J1 is this matrix that was like the inner product of all those guys. So This we have to put subject to linear constraints, the ones that I mentioned before, that the state is normalized, that these guys have to correspond to probabilities, so the sum over A have to add to 1, similarly for Bob, and similarly for like the marginals, like when I sum over A and when I sum over B. And finally, that they are projective operators, so if you project onto different spaces, this has to be 0. And those are the conditions that I put in the previous slide. And finally, that this is positive semi-definite. So what am I doing here? I'm maximizing something, which is the trace of C times a matrix that is positive semi-definite, and I have linear constraints. So that means that this is a semi-definite program. And I mentioned you before that that can be efficiently computed. You just like put the constraints in a computer and then you get an outcome. And we are optimizing over a bigger set than all the strategies that we can have. So in particular, if you have a strategy, it has to fulfill those things. So it means that we're optimizing over a bigger set. And in particular, that means that we're going to have an upper bound to the optimal winning probability. So that's the way that you can have an upper bound for that. And the thing is that now I'm going to show how to like go to the second level. And that is like iterating, and it will be like in an analogous way to just create any level that you want. So we have the set of vectors that we constructed the Graham matrix that was like all the things that you apply to a state. But now consider this guy, which is like all the two things that you can apply to a state. So A times A prime, and then you consider all the possibilities, and A, B, and also B, B, and also BA. So these guys are order 2 terms. So if you consider all of them, you create the Graham matrix of the whole set of vectors, and you impose like similar constraints. And with that, you can find omega 2, which is an upper bound to the winning probability, but we just put more constraints. So it's going to be less or equal than this one. And I want you to have a takeaway right now, in case I was putting too many equations, and I know that that sometimes can be distracting, that if you have a non-local game, by questions X, A, Y, and B, and any strategy that you can have, you have that the optimal winning probability is going to be given by this expression. And like you can just find an upper bound for any quantum strategy that can be computed by an SDP. And this is the so-called NPA hierarchy. And this is actually complete. That the more levels you compute, the closer it will be to the true value, eventually converging. So that's the main takeaway, that you can have any non-local game, you can compute upper bounds that they will converge to the true value. Any questions so far? Okay, if not, I will go ahead. So now I'm going to switch from non-local games to extended non-local games. So instead of having Alice and Bob that share a quantum state, now we're going to have something bigger, that they are going to share a quantum state together with a referee. And now you can see here that the state is going to be shared with the referee, Alice, and Bob. Now the referee is going to get some input, and we'll have like a box, a quantum box, and we'll perform a measurement. So the measurement is going to depend on Z, and you are going to obtain outcome V. So you're going to put it out. And now the winning condition is going to depend, like the description of the game, is going to depend on the inputs and the outputs. So if the relation between the inputs and the outputs gives you 1, so you win the game, otherwise you lose. Okay, and now the winning probability given a strategy, which is computing some A and B for Alice and Bob, and taking the average over X, Y, and Z, is given by this expression. So this is what Alice does, and this is what Bob does. But the thing is that what the referee does is something fixed, something that everybody knows. So this is also part of the description of the game. The thing is that Alice and Bob can at will change the state and the local operations. So the thing is that now in this scenario, we can no longer apply the MPA hierarchy, because there's one party that does something fixed when not optimizing over all these guys. This guy here is fixed. So I'm going to give an example now of an extended non-local game, which is a class of games that are called monogamy-of-entanglement games. And we have the previous same scenario, but now the referee, Alice and Bob, are going to get the same question, all of them, X. So the verifier is going to perform a measurement depending on X, and he's going to have an output A. And the task for Alice and Bob is to guess what is the outcome A. So they both have to take the same answer, and it should be the same as the referee's measurement answer. So to make it more clear, I will go for like a concrete example, which is the so-called PB84 monogamy-of-entanglement game, where the measurement that the verifier is going to perform is like two options. If X is 0, the verifier is going to measure a qubit in the computational basis. And if X is 1, the verifier is going to measure a qubit in the Hadamard basis. So that if X is 0, and that if X is 1. Easy choice, right? So like they're going to have a tripartite state, and depending on the input, the verifier is going to measure his qubit in the computational or in the Hadamard basis. Okay, so this game was analyzed in this paper, and it was shown that the optimal winning probability happens to be the same one as the CHSH game. This 1/2 plus 1 over 2 square root of 2, which is roughly 85%. And the thing is that there's an optimal strategy that was also given in that paper, and it happens to be rigid. Rigid means that like any strategy that achieves the optimal value has to be somehow equivalent up to some local operations, has to be the same. So the strategy is sort of unique up to something. And the strategy consists of the following. The referee, Alice and Bob, will share this state that is just a qubit for the referee, because like the referee is going to measure a qubit, so we need it to be at least a qubit dimensional. And Alice and Bob are going to have a trivial Hilbert space, so no quantum things. And actually this state, why is it interesting? Well, this state is actually like the properly normalized superposition of 0 and plus. So it's a state that simultaneously has maximum overlap with the state 0 and with the state plus. So it has maximum overlap with this guy outcome and with this guy outcome when you measure in X or Y. So regardless of what X is, the Alice and Bob, the players, are going to always answer 0. And that gives you this winning probability. Any questions about this game?
So it means that you must choose the global state size
Yes.
RAB to be close to 0 plus.
No, that's like
0.
proportional to this guy. So this is the properly normalized state of that has this form. So you can choose any state that you want, and the optimal thing that you can do is to send the state that has maximum overlap between the 0 and the plus. So if you were in the blogosphere and the blogosphere was like this, and you had the plus at the 0 here and the plus here, you would take the one that's in between both.
Then how come you can like have the winning probability that corresponding to X equal to 0?
No, that has the same winning probability for both X equals to 0 and X equals to 1. Because like when you take you're always going to say 0, right? So if you take, when you measure in the 0 basis, you're going to have 85% correct. And when you measure in the plus, you're also going to have 85% that you get outcome 0. So you both get like outcome 0 with 85% probability, regardless of X and Y. So that's why you can have a strategy for Alice that is X independent, and also same for Bob, that it doesn't depend on X.
Oh, I see. For the X equal to 1 case, the plus basis you measure correspond to 0, right? And minus.
Exactly. This outcome corresponds to outcome 0. Yes, and this outcome corresponds to outcome 1. Sorry for not specifying that. Yeah.
Okay, good. Thank you.
Okay. So now this is like an optimal strategy for this particular game. And I think that I hope that makes it more clear what an extended non-local game is, which is like these two guys and having a referee. Yeah.
Yeah, so I wanted to ask, like, to clarify, like, in the more general case, I mean, like, because
Yeah.
I mean, so I want to distinguish, because you could have just said that, like, I have a non-local game with 3 players, but obviously this is not the same as that, right? So there's
Exactly.
a special status to the referee. So one thing you
Exactly.
said is like its strategy is fixed, right?
Yeah, like the
But
referee
there's also
performs a fixed measurement. Yeah.
yeah, but there's also more things, right? Because I mean, of course, you call this the referee because in a general game there will be some winning condition, and the
Yes.
referee is allowed to get all the information that's needed to check whether you win or lose the game,
Yes.
right? So that means like the referee is allowed to know Alice and Bob's inputs and outputs
Yes.
in the general case.
Yeah.
Uh, and wait, in the general case, are Alice and Bob allowed to know the referee's input?
No. Sometimes, like the referee's input, it might be a relation between X and Y. In this case, you know that like the referee is going to pick X and send to all of them. If you have the generic case, in the generic case, the referee is going to send them all to Alice and Bob. And usually, like the games that are interesting is that like Z has some relation with X and Y. Sometimes it might be X, but they don't know which one it is. But maybe
Ah,
if you know the distribution of Q, Z, X, and Y, sometimes Z is going to be X or Z can be Y, or like in this case, they are all equal, or it can be the product of them, or it can be the sum. I mean, if it was completely uncorrelated, that would be like less fun. But usually it can be like any. So I just like describe the most general scenario, and this can usually it's correlated to these two guys. If it's not, I mean it might be the case that it's not, but I don't see like nice games that this would be the case. That then you can have applications and stuff.
okay, I see.
Yeah, but here I just described like any generic thing, but usually it would be that there's some correlation between X and Y, that they are not like independent one from the other.
So QZXY is a classical probability distribution
Yes, exactly.
you specify.
Yeah, it's a classical probability distribution.
You need to specify, right? I mean,
Yeah. It's like the distribution
Yeah, I
is
think
known and the description
yeah,
of the
it's
game
known.
as well.
oh,
Yeah.
I see. Okay, good.
All right. So now, well, this is what I already talked about. So I'm going to get back to the generic case where we had like a Z, X, Y, and then any answers. And you know, like this is the winning condition of the game, depending on the inputs and the outputs. And the optimal winning probability is going to be given by like the normalization over like the inputs and then the probabilities that you can reproduce. And we're just now here summing the ones that win, which is equivalent to summing them in the front. And here now again, I'm considering operators that are not tensor product, but that commute. And well, this is what the verifier does, this is what Alice does, and this is what Bob does. And the thing is that you can write the same expression again, but instead of writing the sandwich here, the inner product, you can write it as a trace of this guy. This is essentially because of cyclicity of the trace. This guy, you can put it in the front, and then this becomes a number. And I hope that this is clear, that like, these two expressions are equivalent. But here now we're going to have a density matrix. And now I'm going to define this rho tilde density matrix, which is having this guy here, but without considering what the verifier does. You see that this is like the same thing, and now I'm just tracing out A and B. So this is a positive semi-definite matrix, and this is essentially the unnormalized quantum state after Alice and Bob did the actions. So Alice and Bob applied something to the quantum state that they have, and the verifier didn't apply anything yet. So that would be like the local point of view of the referee if you trace out Alice and Bob. And the thing is that with that definition, the winning probability can be rewritten as this expression, V times this guy. And now I'm going to consider a matrix, and I'm going to label the entries like XA and YB. And I'm also going to introduce some parameter epsilon, which will refer to identity. So if we consider this matrix, this will correspond to this guy that we have in the front, but instead of like here having A times B, depending on X and Y, we're going to have that epsilons are going to mean that they apply the identity. And similarly, if I just put one epsilon and the other one, it means that Alice applies something and Bob does the identity. And same for this case. So epsilon here means that here we're going to have an identity and Bob does something depending on Y and B. So now, what this matrix need to fulfill if we are considering quantum strategies. So this is going to be very similar to what I described before with the J matrix, the G matrix. So first, we need that the quantum state is normalized. So we will need actually that when you take the trace of this guy here, because this is like the trace AB of this state. So if I now take the trace of this guy, this needs to be 1. So it means that this element has to be 1. So similarly, now if I consider, and sorry for the long expression, but if I'm considering these guys here that are just like Alice applying something, when I'm summing over all the outcomes, this guy has to be the identity because like we are considering this to be a measurement, so it has to add up to an identity. So this guy has to be the identity, what I wrote here. And if I write it in terms of this matrix that I'm defining right now, so it means that the sum over these guys has to be this entry here, the identity. And something else, I'm also want to consider these guys to be projective operators. So if I project onto different subspaces, they have to be 0. So that's what I recopy here. But if these guys A and A prime are the same, so this guy has to be like a square to itself. So that means that these matrix elements have to fulfill this equality. And finally, similar things like A and B have to commute. So when I'm taking this trace AB of these guys, so A times B has to be the same as B times A. So this is equivalent to just like in the terms of this matrix that I'm defining here, that XA YB has to be equal to the entries YB XA. And now I'm just going to do a comparison. So now we have to maximize this quantity, and this I'm going to call omega 1, subject to 1, the linear constraints that I just mentioned to you guys, and 2, this guy being positive semi-definite. So we're having again one optimization over a positive semi-definite matrix subject to linear constraints. So that's a semi-definite program again. And now I will just do a quick comparison with the NPA hierarchy and the extended NPA hierarchy. If I consider a density matrix for this state, which is L dimensional, so we're going to have L columns and L rows, the NPA hierarchy for a regular game and the extended NPA hierarchy are going to be compared as follows. So I define first a matrix G1, and then we're having the inner product of these elements. So I was constructing it like this way. And in here, we were having the probabilities of outputting X and B given X and Y. And we could find an SDP that was like an upper bound for the optimal winning probability. And this actually, the set of like levels of the hierarchy was converging to the true value. Now we have a quantum referee that is L dimensional. So I'm defining a matrix M1, and the measurements are going to have these L squared blocks. So they are going to have blocks. And the thing is that now I'm going to define a larger matrix that is going to have a block per like any of the entries of the matrix that the verifier is going to have. So first, I'm going to have gram matrices here. So like, don't get scared now, I'm just going to put all the inputs. So I'm going to find a bunch of like block matrices, and this one would correspond to these guys, but now we're going to have a block matrix for each of the entries that the verifier's measurement will have. And the thing is that in the same way that we could extract probabilities from here, now we'll be able to extract some probabilities from this guy. And actually, it will be from these guys that I just like highlight here. So the probabilities to get these outcomes given these inputs are going to be given by tracing out what the referee measures and what Alice and Bob do to the state. Is that clear? So the thing is that this is a trace, so it's just summing over the diagonal elements of these guys. And the diagonal elements, we have them here. So with that, we have like a semi-definite matrix, and we can like compute an outcome. And since we're optimizing over a set that is as well larger, because it's like every strategy will have to fulfill those conditions. So we're optimizing over a superset, we're gonna have a larger value or equal to the optimal winning probability. And the result of these guys is that also this actually converges to the true value, to the true optimal value of the non-local game. Questions?
So
Okay.
if
Yeah.
if the referee does trivial thing,
Yeah.
does
If the
nothing.
referee does, yes, then we're back to this scenario.
Yeah, okay, makes sense.
Yeah. Yeah. But if the referee does not something trivial, we have like a block matrix per each. So here, like it might be a bit confusing, but now I just want you to have in mind that we have a matrix that we are optimizing over, and here we have a matrix that like the size is like depending on the size of the quantum referee. And in both cases, we can compute a semi-definite program. In this case, this matrix is going to be larger, but the thing is that you can still compute it to find an upper bound. Okay, so the main takeaway is that you can have any extended non-local game described as follows, like inputs and outputs. And then like you can have any winning probability that can be upper bounded, like whatever Alice and Bob do, by this guy, omega 1. And the thing is that like the important thing is that that is something that you can compute by a semi-definite program. And actually these guys, like the more levels you put, the better will be the bound, and it will eventually converge to the true value. Okay, so that's the big takeaway. So what is our contribution? So I'm going to go to Lossy games. So assume that we have the following scenario, and I'm going to introduce a motivating example. So the Lossy BB84 monogamy-of-entanglement game. So we're going to have a monogamy-of-entanglement game, which I recap, it was described by like all the parties having the same input and having to guess what is the verifier's measurement outcome. So they have to ideally output the same. That has to be this result. So what if the state that they share is like it was prepared at some point beforehand, and like the referee gives a part for himself, and someone sends like a part to Alice and sends a register to Bob. So the strategy that I mentioned before, it was to use this state that was the one that has the maximum overlap between plus and 0. And here you're going to like also send, for instance, two auxiliary qubits to Alice and Bob. And they always have to answer 0 because that's what gives them the optimal winning probability. And a way to do that is, for instance, to measure the qubits in the computational basis. I mean, you're always going to have 0 if you have the 0 state, right? So the optimal winning probability is this roughly 0.85. But okay, now if you play it many rounds, so you're going to collect all the correct answers, you put them in a sack, and you also collect the incorrect answers, you put them in a sack as well. And it should be that roughly 85% go into this sack, and the rest, 15%, go into the incorrect answers. Okay. But what if, for instance, you are using a quantum channel, like let's say an optical fiber, that has some loss? And well, like fibers actually have quite some loss. So you send a photon or any other way to encode the quantum information, but it gets lost on the way. And same for Bob. You send it to Bob and it also gets lost on the way. So assume, for instance, that we have a lossy channel and 50% of the quantum messages get lost. So now in this scenario, we also have to consider the possibility that Alice says, okay, I'm sorry I did not receive my message, so I cannot answer. And same for Bob. So now, if we consider only correct and incorrect answers, we're going to have that 50% of the previous ones are going to be correct. And if you put in another sack all the incorrect ones, so it's going to be the rest. So the thing is that this is kind of bad in some sense, because like we put in the same box all the incorrect answers and the no answers. But what if we add a third sack and we put all the ones that are lost? So now we're going to have the 50% go here and only 7.5 go to incorrect. So that should be what you expect if they fulfill like this strategy. But in this sense, if Alice and Bob are dishonest, and they, instead of like being here, for instance, they are in another location and they actually get all the photons, they can have a cheating strategy. And the cheating strategy works as follows. So they prepare the initial state that is state 0, for instance. And if they get x equals 0, they answer 0 because they know that the referee is going to perform a measurement in the computational basis. So the output is going to be 0. So it's going to be correct. But otherwise, they just say, like cheating, that the photon was lost. So the thing is that the first thing will happen with probability 50% if like x is picked uniformly at random. And the second one will happen with probability 50% as well. So now they are going to fulfill that 50% of the messages will be lost, but 50% will be correct. And the important thing is that they will not have any incorrect answers. So in all the conclusive rounds, they will always be correct. Do you have questions about that? So I'm showing that loss is also something that some players that can use some cheating strategy can take advantage of to like perform better than they are supposed to. Okay, this one was kind of easy, 50%. Yeah, but what if like the loss is something a bit more random, like 31.2? So our contribution is as follows. So you have any extended non-local game, and you have this following scenario. If you have a certain loss for Alice, so a transmission rate eta 1, and a certain loss for Bob, a transmission rate eta 2, so that they can also answer sometimes that the photon was lost with this perpendicular symbol, we have the following result. That the winning probability, the optimal, can also be upper bounded by something that can be computed by a semi-definite program. And eventually, we have that also these guys, you can have a hierarchy that in the limit converges to the true optimal value of this game. So like, what is the best that they can do if they can, in a cheating way, take advantage and say, I don't know, the photon get lost, even if they didn't lose it. So for instance, in the example that I said before, so what if instead of having this 50%, you have like the 31.2%? So now we got that the optimal that they can do by computing a semi-definite program and obtaining the first value is like this bunch of numbers. 43%, 25.8 incorrect, and 31.2% lost. So the thing is that they are no longer be able to reproduce answers that are never incorrect. So they actually have to be incorrect sometimes. Any question?
Is this
All right.
easy to see?
Oh no, this is not. You have to like compute a semi-definite program to see. Actually, I'm going to show in the next slide that like, regardless the loss, you can just have this game. You put the parameter, like the transmission rate, and you compute a semi-definite program, and these are the outcomes that we obtained, like varying this parameter eta, what is the best that they can do. And this is actually 50% loss, but the thing is that you can see that at the end, if there's no loss, we recover this 85% of winning probability. And then the thing is that you just need the parameter you put it in a computer, and you get a number out of it. And this has applications, and I'm going to show one application that is to quantum position verification. So I don't know if you've heard of quantum position verification. Otherwise, I will just like briefly introduce it. So quantum position verification consists on the primitive of verifying someone's location. Assume we have a prover that claims to be at a certain location. And the thing is that two people don't trust this prover. So we're going to have two verifiers that are going to challenge the prover, and the prover has to send some messages back. And if like the prover performs something correctly, the verifiers are going to say, yes, you are in the correct location, or no, we don't trust you and you are not in the location that you claim to be. So for that, I'm going to show a specific protocol that is the QPV BB84 protocol. And then we have the position arrow that's going to be verifying the location in one dimension. And we have a prover that is supposed to be at this location. So two verifiers are placed at the left and at the right of the prover. And I'm going to plot the time arrow here. And at the beginning of the protocol, so the verifier prepares the maximum entangled state. So that it's like the 0, 0 plus 1, 1 and normalized. And sends one register, one qubit to the prover and keeps another qubit for himself. Whereas, like the other verifier, at the speed of light, all the communication should be at the speed of light, sends a bit 0 or 1. So the thing is that if you send things at the speed of light, this position P should be the first one that you have the two information. Otherwise, if you are here, you cannot have X, whereas you have P, because like X will arrive here later on. And if you're in any other location, you cannot have both informations. So now here you have to perform a measurement depending on X. That is going to be measured in the computational basis or measured in the Hadamard basis if X is 1. And then you just broadcast the outcome. The thing is that like you're going to measure half of an EPR pair, and the verifier is going to do the same, measure half of an EPR pair in the same basis. So they should get the same outcome. If both answers are the same and equal to like V0's outcome and arrive on time, at the time like is sent by the speed of light, the verifiers accept. And now I will just show how an attack looks like. And I think that with that, I will just skip the rest because I think that I'm like almost on an hour now. So if you do not pressure entanglement, assume that like we have this position scheme where we have the position and the time arrow. And then instead of having a prover in the middle, we're going to have two people that are not in the middle and want to attack the protocol. So they just want to make the verifiers believe that there's someone in the middle, whereas in reality, there's no one in the middle. So the verifier is going to perform the protocol in the same way. So prepare a maximal entangled state, send one part to the prover and keep a part for himself. And the verified one is also going to act in the same way, send a random bit X. And the thing is that Alice is going to intercept P, the one qubit. She can perform an arbitrary quantum operation, and she will keep a register for herself and send a register to Bob, whereas Bob, it can be argued, and then I can argue it a bit more if you're not convinced, that without loss of generality, what he can do is just to copy X and send a copy to Alice and keep a copy for himself. Now at this position, like I pointed here, they have a tripartite state that is shared. And the verifier is going to perform a measurement that is publicly known, that depends on X. And the thing is that we get an answer A. So what do they want to do? Alice and Bob, what they want to do is to answer the same A as the verifier. So that has the flavor of a monogamy-of-entanglement game, an extended non-local game that I was mentioning before. Because like there's a verifier that's going to get an input X and output A, and Alice and Bob get the same input and want to guess what is the outcome of the verifier measurement. So this can be lossy if you also apply that like this photon that you send here can be lost with a certain probability. But now, like Alice and Bob are not going to be placed here, so you know what is the transmission rate from here to here. But if they are at any other arbitrary location, they're going to have less loss and maybe you can just be close hereby and have almost no loss. And then they can use that for their advantage. So with our semi-definite programs that I mentioned before, you can compute security for this protocol. And actually, if you put the numbers, we can have this plot that if the error and the transmission rate that you have are in this area, you have that the protocol is secure. And otherwise, you have that there's an attack for the protocol and the protocol is no longer secure. Questions about that? Okay. If not,
wait,
now,
can I clarify the error? Wait, the error is what is the x-axis?
Yeah, the error is like the probability that these two guys are different, whereas they still have to be the same. Like it means, for instance, that you here have a device that actually you are being sent a 0 but with a certain probability the device is going to output 1.
Oh, okay.
Yeah. So if you had to measure, you receive the get 0, for instance, and your measurement device has no infinite precision and also not infinite accuracy, and you can measure the qubit with a certain error. So that's the error that you can have like in the measurement device, which essentially would be like the probability that this guy and this guy are different, even if you implement the protocol in an honest way, but due to the laboratory constraints that you can have in your equipment.
Right. Okay, thanks.
Okay, good. Thank you. And now I'm going to go to something else that is like I mentioned lossy games and I showed an application. Now I'm going to go to constrained games. So, and I'm also going to use the previous example, which is the BB84 monogamy-of-entanglement game. And where we have the scenario that all the parties get the same inputs, and here they should output the same thing. And if you don't put any constraints, so like a regular game, the optimal winning probability is like this 0.85. And this was attained by this strategy that I mentioned before, which consists on Alice and Bob preparing this state and outputting always 0, regardless on the input. So now, what if we impose the following constraint, for instance, that the probability that Alice and Bob answer different has to be at least some epsilon. So this discards this strategy because like they always answer the same. So can we still achieve the optimal bound if we have another strategy that has a certain probability of answering A different than B? So that would imply that there's a different strategy that attains the optimal value. And well, we know that this strategy is rigid. It was proven. So it means that the answer is no. And actually, we can impose the constraints and the optimal winning probability depending on epsilon. If epsilon is 0, we have 0.85, and it's like this like round points here. But the thing is that the more you have to impose that the answers are different, the lower is the winning probability. And actually, this optimal value could be attained by something that uses no quantum resources from Alice and Bob. But if you put more error, if we optimize overall strategies that don't use qubits, that just send one qubit to the state, to the referee, we have that this is significantly lower than the upper bounds that we get. And we actually showed that like it is required that Alice and Bob have qubits to attain this constraint and attain the optimal value that is given by these points. Okay, so that is a way to constrain a game and see what happens when you do so. And I think I'm a bit running over time, so I might go quick to the next slides, or I can also go to like a recap slide right now. What do you guys want?
Depends, like how much more do you have?
Still a few minutes, so I can probably just directly wrap up because that would take me like 15 more minutes or so.
Oh, like for the rest of the thing.
Yeah.
yeah. I think we probably don't have 15 minutes.
Yeah.
If it
no,
was like
okay.
5 minutes, maybe.
No,
Okay,
yeah, no, I think that
great.
it would take me, because I see that it is already taking me longer than I planned, so I can just skip a few things and go for the main takeaways.
Okay.
So yeah, the thing is that like this can be useful to put constraints if you want to see two scenarios. And one natural constraint is that if two people pretend to be one person, that you impose that the answers are never going to be different. So that's a natural constraint of a protocol. And like the main result that I wanted to state here that we also had is that if you have any set of constraints that you put to a game, for instance, that they can never answer differently, or that they have to be subject to some error because your experimental constraints say so, you're going to have that the optimal winning probability can be actually also upper bounded by computing a semi-definite program. And not only that, but also this eventually will converge because there's a hierarchy to the true value. And we could show that most of them actually converge quite quickly. And now I'm going to skip relativistic bit commitment because that's one of the applications that we could find. Sorry, I'm going to go through it quite quickly. And yeah, we had some results about relativistic bit commitment and also about quantum key distribution, but I'm also going to skip that. So the main takeaway that I want you to have is like, okay, you consider a protocol and then you have like what laws do you have in your laboratory? And also what natural constraints does your protocol have? And if you can reduce its security to extend a non-local game, you merge these two things. And then you compute a semi-definite program and you get some security upper bounds that you know that will actually convert to the true value of the security of your protocol. So all you need is like to know the parameters that you have, the natural constraints, which might include errors and stuff, and also the laws that you have. And then you can get security by computing semi-definite programs. So some other problems that we still have is like other protocols that we can apply these techniques, because I mentioned quantum position verification, I mentioned QKD, and I mentioned relativistic bit commitment. So if you can find other primitives. So also optimizing the code that we provided in our paper, making it more efficient and more like easy to handle for people that want to directly apply our results. And also finding analytic results would be nice, because like all of the results that we get is like from computing a semi-definite program in a computer. And I don't know, any other thing that you might come up with. And with that, I would like to thank you for your attention, and I hope you enjoyed the talk. Thank you very much.
Okay, thank you very much. It was a wonderful and very informative talk. Yeah, so I guess we're sort of slightly over the time, but we can probably still entertain like one or two questions from the audience.
Yeah, definitely.
Yeah. Okay, maybe I can start first. So when we talk about these games, so you have rounds to these games. So okay, try to understand. So this computation will give me the winning probability if you have like playing these rounds in parallel. Is that the correct way to interpret it? Or is it sequential?
It is sequential, yeah.
Okay.
So yeah, the thing is that also you can put a semi-definite program for the sequential repetition of the game, and then you will get outcomes. But the thing is that it depends on like the particular game. So in particular, like a sequential repetition of another game, a parallel repetition of another game is like a new game somehow.
Yeah,
so you can also put it in there. Actually, one of some results that we have is like computing parallel repetition. And I'm just going to show like quickly one plot that I have. That is actually, we compute like for one repetition of one game, 2 repetitions parallel, 3 parallel, and 4 and 5 parallel. But the thing is that the more parallel repetitions that you put, the bigger is the semi-definite program.
It's
and
harder
yeah, the computer took some days to compute the last value, because that's a big that's the downside of this, that like it depends on n, and then you have a very large matrix, and it is like you can still compute parallel repetition things, but the thing is that the scaling is bad.
Ah, yeah, okay. But at least in principle, it's doable.
Yes, theoretically
Yes.
it is doable, yes.
Yeah. Yeah. So, and then maybe just one question. So when you said something this constraint with the like Alice and Bob in this
Yes.
monogamy-of-entanglement game,
Yeah.
so because the NPI hierarchy will not tell you the dimension of the strategy. So how are
Exactly.
you able to make this 3-qubit claim and so on?
Like one thing, sorry. So
No, I mean
yeah,
like you were making a claim. So when you had this plot in the constraint case, yeah, here. So how do you know this 3-qubit? Like because that will not
yes.
come from the NPI hierarchy, right?
No, that's like that was sort of optimizing. So I first saw these values, like the black points over here. And then I did an optimization over all the strategies that are like that Alice and Bob don't use any quantum things. So that are like this, that they then just the referee has a quantum thing. So the total state is a 1-qubit state. And then this optimization was giving these values that was significantly lower. Then what I did is another optimization, but now the referee and Alice share 1 qubit, well, each, so they share 2 qubits. And I did an optimization and I got this line, an optimization over all the POVMs that they can perform with 2 qubits. And I was seeing that, yeah.
Like how, but nothing in the optimization would force you to specify the dimension, right? So what do you mean
actually,
when they?
I was taking generic 2 qubits and I was optimizing over all the possible measurements that Alice can do. And I was seeing that with that, you can attain like the same values that you had as an upper bound.
Oh,
So
okay.
yes, and I was saying, okay, you have a generic 2-qubit state. Referee does this measurement, and I'm optimizing over Alice's measurement.
Okay. Now I see.
Yes.
So there's like 2 different computations. You're comparing them.
Exactly. And
Yeah,
also, I was putting
the
the constraint that the answers have to be at least this different. And also, like, you needed 3 qubits to go beyond that and to match the upper bounds that we provided. So that's sort of a funny thing because, like, if you don't have any error, you can do it without qubits, but you actually need to use quantum states and measurements if you have to fulfill certain constraints. So that could be, for instance, a way to like first discard like rigidity, but also if you put certain constraints, it would be a way to force players to use quantum states instead of not using like they do here.
Yeah, that's quite surprising. I don't even have any intuition why
No,
that
at all.
happens.
Yeah, no. I also got a bit surprised because I expected this to be attainable without quantum power from the
Yeah, I
tablets.
mean, like at least like I would imagine maybe some classical thing that they can do.
Exactly.
Sorry.
But yeah, here I optimize over all the classical things that they can do, and it is like significantly lower than the optimal value that is actually attainable. So that actually means that these guys are tight only computing the first level of the hierarchy, because it could also be possible, could have been possible that actually this was the first level, but the second level was giving an upper one that was lower. But that is kind of great because we're showing that usually the first level already gives you the tight value.
All right. Yeah. So I don't know if other people have questions.
Yeah, thank you for the very nice and wonderful work. And so I'm just curious because I didn't follow the cheating part.
Yep.
Yeah, so it looks to me I don't fully understand why the incorrect answer can be 0 when the cheating the lossy is 50%. It looks kind of more strange to me if the incorrect answer can be like totally removed.
Yes. So if I go, for example, I think that like this QPV attack is more illustrating. You send a qubit and you know that, for instance, like it will not arrive here to the prover with probability a half. So from the verifier's point of view, you're going to expect that half of the times they say that the photon was lost. So Alice, in a cheating way, she can be placed here and always intercept the qubits. And then she can measure the qubit in the computational basis, right? And after communicating, they know if like the computational basis was the correct basis to measure, which will happen with probability 50%. If so, you answer the outcome that you got, and also Bob, because like Alice will send it to Bob. Otherwise, they both know that they measured in the wrong basis, so they are just going to claim that the photon was lost at will. So whenever they answer, they will be correct, because they just guess what is like the X. And if they say photon loss, they will do it with probability 50%. And that's like actually what the verifier might expect from this case. Is it?
Kind of something, but I need to think it over again. Yeah.
Yeah, it is essentially that if they are not here and they don't lose the photons that prover is expected to lose, you can just sort of guess what is X. And then like when your guess is incorrect, you send photon loss. But if your guess is correct, you know that you did the correct thing to do at the beginning. So you can winningly claim that the photon is lost when you never lost it, because you actually did something to the qubit. And like 50% of the time you can do that, right? So if with 50% you're going to be correct and 50% you're going to be wrong with your guess, you can always say half of the time 50%, and the other 50% you know that like you did the right thing.
Okay, so you can know if you answer correctly, right? So you just
Yeah, because after you know what X was, you know, for instance, if you did the right thing or not.
I see. Okay, good. Okay, thank you.
Actually, in this case, like the thing that's more confusing to me is, so in the 50% case, or like the sort of the large loss case, I understand sort of like I can follow from the strategy why it works, that you're never incorrect. But if the loss is less, then now sometimes you're incorrect. That's more confusing to me, actually.
No, but yeah, that is good, because that's precisely what gives us security for this protocol. So if the loss is less than 50%, let's say the loss is
okay,
0.
yeah, I guess that's true. Yeah, you're right. So in some sense, yeah, like in a typical protocol where at least if it's not too lossy, then it's sort of still secure.
Exactly. That is the thing, that if it's too lossy, it's not secure, because they can just take the loss at advantage. But if most of the photons arrive there, so this is going to be more secure. Yes. Yeah, that's the right way to see it, I think.
And just to clarify, because the way that we discussed this is you looked at the lossy case and then the constraint case, but
Yes.
of course you can have together.
Yes, exactly. So also, if you have them together, you still have that this can be upper bounded by a semi-definite program, and also the convergence still applies. So you can have a protocol that has everything together, right? That has laws, and you want to impose some constraints. And then we will have that also, we can find an upper bound that will eventually converge to the true value of the game.
And the only constraint on the constraints is it has to be a semi-definite constraint?
No,
or maybe
you can
it
put
has to
any
even
constraint.
be linear.
No, you can put any constraint on the probabilities that you
it doesn't
expect,
have
because,
to be linear?
well,
I
I mean,
imagine it has
yeah,
to at least be linear.
you have to put some linear things, right? I mean, of course, you cannot say that the square of the probability is something like that, right?
That was what I was wondering. Okay, that
no,
won't work,
yeah. It has to be linear. Yeah.
But at least like it can be any linear constraint.
Any linear constraint, yes. Yeah.